Thanks a lot for the invitation. Today what I'm going to present to you is a paper that is joint work with my colleague Anthony Hayes and our PhD student Nikolai Cook. Over the past 20 years, or at least 30 years in economics, there's been what some people call a credibility revolution. Just meaning that economists have been trying to use experimental and quasi-experimental methods more and more to try to move from correlation to causation. So economists are using more and more RCTs, instrumental variables, difference and differences, and other methods. And some authors have been I've been arguing that this is very good, and that because of this, causal inference might be better. And nowadays, these methods that have been, or are usually seen as gold standards. So you need to use these methods if you're doing empirical work in economics. What we're going to be interested here in this study is a different type of credibility. So there's this credibility that maybe internal validity is going to be very strong with these methods, but at the same time, there's this growing literature that you guys are aware of that shows that there's, the extent of publication bias, the extent of specification searching, p-hacking might be quite large. So what we're going to be interested in is sort of looking at credibility, but from this point of view. So we're going to be looking at papers using these methods, using these experimental, quasi-experimental methods, and trying to look at the extent of p-hacking or specification searching by method. Okay, so this is what we're interested in this paper. And in a sense, we care about this because we're worried about false positives. So maybe papers that are getting published suffer from publication bias, but even papers that end up being published in top journals in economics might suffer from these false positives. So maybe the use of these methods, the use of these four methods that I will talk to you about in this talk, might not have decreased the extent of p-hacking. Okay? So this is what we're interested in. What we're going to be doing is to manually collect test statistics in 25 top economic journals. We're going to be interested in looking at main tests, so the main coefficients of interest, and we're going to be looking at the distribution of Z statistics in published articles in economics. All these articles are published in 2015, but they've been written in maybe 2010, submitted in 2012. So think of articles that were published in 2015, but have been written a bit before. So this is going to be important going forward. And what we end up with is something like 300 articles. So we read these articles, and then we looked at the tables and just manually collect all the test statistics in these tables. Okay, so that's what we're doing. Some people in this room are not economists. I'm not going to spend a lot of time on explaining what is RCT. I think we all understand what is RCT. But I will spend a bit of time trying to give you an idea of what is an IV in economics, what is an RDD. So it might be clear for political scientists, for economists, but maybe not for everybody in this room. The RCT papers that we have are not lab experiments. There are very few lab experiments. These would be lab experiments, but in the field. So I'm really talking about like RCTs in Kenya or somewhere in the US, mostly in development economics or health economics. So RCT, experimental, and the other three methods are going to be quasi-experimental methods. The second method that is used in economics more and more is RDD. The key word is going to be discontinuity. So what we're interested in when we're using these methods is to look at a cutoff and a threshold. So for instance, winning an election. So if the Democrats get more votes than the Republicans, then the Democrats, as for instance, if we think about like at the state level, so your Gardner is going to be, okay, so maybe there's a, okay. Anyway, so imagine we're interested in what is the effect of having a Gardner that is Republican versus Democrats. If you do regression discontinuity design, you're just going to look at close elections, so election won by a small margin versus election lost by a small margin. So the analysis is very local, and maybe we gain internal validity by doing this type of analysis. So anyway, this is RDD. We're going to be looking only at sharp RDD, so we exclude all the fuzzy RDD, where you use, in a first stage, an instrumental variable. Okay, come back to this. The other two methods, diff and diff, difference and differences basically is on RCT, but it's non-experimental. We exclude all the difference and differences papers that use a submethod, like matching. So if you do a definitive, but you also use matching, we're going to discard these studies. And the way you want to think about it is just analysis where you have a treatment group, control group, you do before and after for treatment group, before and after for control group, and you look at the differential effects. The last one, IV. IV is really hard to explain to non-economists in 30 seconds. So let's say you're interested in the effect of growth on conflict, and you have a cool instrument, which is rainfall. Thank you, Deb. So we're doing this paper in which we're interested in agricultural production in sub-Saharan Africa. We're interested in the effect of this X, this endogenous variable, on the likelihood of conflict. But now, obviously, you cannot really randomize growth. So what you're going to be using is sort of a variable, an instrument, that is going to exogenously change your X. And you're going to be using something like rainfall. So you're in Nigeria, 1 year it rains, lots of growth, lots of agricultural production. What happens to the likelihood of a conflict? Versus a year where it doesn't rain, you don't have a lot of growth. So this is an instrumental variable. What is interesting with an instrument is that you're going to be doing 2 stages. The first one is your instrument on agricultural production, on your X. So that's going to be the first stage. And for unknown reason, you need an F-stat of 10. So again, these papers were published in 2015. Back then, 10 was like the magic number. You need at least 10 in the first stage. And then the second stage is just your relationship between X and Y. So that's going to be the test statistic that we're going to be collecting. Okay. I'll show you some stuff with the F-stats later on at the end of the presentation if I have the time. 25 top journals. We exclude Journal of Economic Literature, Journal of Perspective Economics. So we end up with like top 30 journals or top 32, and then we pick 25 journals. What I want you to think of is, imagine a journal like JPubE, Journal of Development Economics, AG Apply, Restat. So these are the journals that publish a lot of papers that we're going to be having here, or AER. And the analysis is going to be mostly with journal fixed effects. So what I want you to think of is a journal. Think for the presentation something like Journal of Development Economics. When there's a Journal of Development Economics issue, or they publish some articles, we're going to be looking at these articles, and the question we're asking is, are articles using an RCT more likely to reject the null hypothesis than an article using an RDD, or a diff and diff, or an IV within a journal? So we're looking at the extent of, are you able, what is the extent of rejecting the null hypothesis by method? And we're going to be using Caliper tests, so looking at whether there's bunching just at 1.96, okay? So we have these journals, we collect coefficients of interest. We're going to be collecting a lot of test statistics. We exclude all robustness checks, so if a table says robustness check, or in the text, the authors say, well, this is a robustness check, we exclude it. We exclude constant, we exclude appendices, balance tests. So we're interested in coefficients of interest. Coefficients of interest, if you do an RDD, you're going to report many, maybe for many different outcomes. So we're going to be collecting a lot of tests in a given paper. Okay, so if you do analysis by socioeconomic groups, we're going to be collecting all of these test statistics. So it's not only one test per article, it's going to be many tests per articles. But these are not controls, they're not robustness checks, okay? Some articles are using multiple methods. So think of a paper using an RDD, but there are some tables where they do a diff and diff. We're going to keep these articles. It's robust if you exclude them, but we're going to keep those. And the articles that are the test statistics that use the RDD are going to go for the RDD sample, and the ones that use diff and diff, they're going to go for the diff and diff. Okay? Now, that's the main result of the paper. So the rest of the talk is a bit useless. It's going to be about regression, robustness checks, trying to convince you that, yes, please go ahead.
Where do you put the broken RCTs? Are they instrumental variables?
So it's a very good point. So if you do an RCT and you have partial compliance, you do an intention to treat, that's the RCT. If you have a first stage where you use an instrument, that's an instrumental variable. Thank you. Okay, so that's the main results. What I'm showing you is the distribution of Z statistics by method. So there's 4 graphs, there's 4 methods. And we're showing you the range going from Z-stat from 0 to 10. There's also Z statistics that are greater than 10. Most papers in economics, what they do is to report the coefficient and standard errors. They don't report the p-value or the t-stat. about 10% of papers report the p-value or t-stat. So here what we do, we take the coefficient divided by the standard errors to get the z-stats. Okay? And then we're just plotting these by methods. What we're going to be interested is whether there's bunching, whether there's a mass at 1.96, at 5% level, or at 10% level, or at 1% level. Okay, so just take 5%, for instance. What we see is that RCT and RDD, the bunching at 5% level, is much less than for IV. So if you look at IV, for instance, the maximum is exactly at 2, at 1.96. So what you get from this, you can interpret this the way you want, but what you get is just that IV papers are more likely to reject the null hypothesis, especially around the critical values, than for RCT or RDD. Let me first say that this idea that RCT might be, you might be more likely maybe to publish a paper not rejecting the null with RCT is not something new. So we've shown this in other studies. Eva has also been working on this. But this idea of looking at diff and diff, IV and RDD is very, well, let's say it's novel. So we're the first ones to actually show something like this. And this pattern for RDD is something I was not expecting at all. And I think a lot of people were not expecting this. Okay, so we can talk about like what's going on, why do we find this. But before doing this, let me just convince you that controlling for authors' characteristics and articles' characteristics doesn't explain this pattern. Okay, so it doesn't seem to be explained by characteristics of authors. So top people are more likely to use RCT. They can publish negative results versus people from less well-known universities are going to be more using IV. That's not explaining this pattern. Okay. We use different methods to document the extent of p-hacking or just bunching. What I'm going to be showing you is Caliper test, but we do other exercises in the paper if you're interested. The regression we're running is whether the test is significant at the 5% level or at the 10% level or at the 1% level. I'm going to show you 5% level, but we do it for all the critical values. So here, it's a given test in a given journal, whether it's significant or not at the 5% level, whether the z-stat is greater or equal than 1.96. We're going to have journal fixed effects in some models, and what I'm going to have is a dummy saying whether the test is a diff and diff, the test is an IV, or it's an RDD. So the baseline category is an RCT. You can use RDD as a baseline category. You're going to find very similar estimates. We cluster centers at the article level, and what we're going to be doing is to restrict the analysis at the just below and above a given threshold. So doing a basic Caliper test. That's for 5% level, so we end up with a sample size of 3,000. In the first column, there's no control, and again, the dependent variable is whether the test, the z-stat of that given test is significant at the 5% level. So what you see is for this sample, the mean is about 0.5. So an IV test, the likelihood that it rejects the null hypothesis is about 58%, whereas for an RCT, it's about 48%. So there's a gap of like maybe 7–10% in the likelihood of rejecting the null hypothesis. Okay, so this is only at the cutoff. And the effect is significant for IV in comparison to RCT. For diff and diff, it's not significant in the first specification. Then what we do is to start to include controls, trying to explain this. So I'm going to be controlling for whether at least one of the authors is a female economist. So the likelihood of having a female economist is about 0.5. Controlling for things like solo authored, controlling also for whether one of the authored or the share of authored at top institutions. So MIT, Cornell, Berkeley, Stanford, etc. So pretty much everybody on the program except me would have a 1 for top institution. Then I control for articles characteristics, citation, reporting method, table ordering, whether it's the first table in the paper versus it's the 20th table. Maybe you change your behavior depending on which table it is. Maybe you're more likely to not reject the hypothesis in table 5 than table 3. You can stick to the first table, the results are very similar. But here I'm just controlling for this. Reporting method is only whether you report it as a p-value versus a t-stat, etc. Then I'm going to be controlling for other journals characteristics, whether it's a top 5, so there are 5 top journals in economics, and here a journal fixed effects. And then in the last column, I'm going to be controlling for, I'm going to put the same weight on every single paper. Some papers have a lot of t-stats, others don't. And if you do this, it's pretty stable for IV. So the effect is still significant. You're more likely to reject the null hypothesis than for RCT and RDD. For definitive, once you start including controls, it's positive and significant too. We do a lot of robustness checks. So what I showed you here was probit with marginal effects. Logic models very similar, OLS very similar estimates. You can play with the weighting scheme. You can play just restricting the sample to the first table of the paper. You find very similar estimates. You can also play with the window. You can do it at the 10% level. The estimates are very similar. At the 1% level, we don't find anything. There doesn't seem to be an effect of using different methods for the 1% level. So most of the action is for 10%, 5% level. And here what I'm going to be showing you is instead of showing you tables, I'm just going to show you but with these graphs again. But here I decompose this, the sample depending on articles characteristics or author's characteristics. Here I use the median number of citation as of 2 weeks ago, so number of citation that these papers got in 3 or 4 years after publication. And I'm going to be interested in comparing papers that are cited a lot versus papers that are less cited. And if you look at the pattern, it's quite similar for this type of articles. So it doesn't seem to explain what's happening here. Okay? You can do something very similar with top institution. The only thing you seem to find is for RCT, people like, Ted Miguel, Esther Duflo, etc., they're more likely to, they can actually publish an RCT that doesn't find an effect. Whereas maybe some people might not be able to do this in top 25 journals, okay? Which is really good. Whereas for IV, again, somebody not at the top institution like me, the likelihood that it's significant at the 5% level is slightly higher. But again, the pattern is very similar and doesn't seem to be explained by these characteristics. You can do it by number of authors, by gender, by many things. So now we're coding whether the author is really experienced depending on when they finish his PhD, or whether he's tenured or not. I'm not going to show it to you. We're doing it right now. Okay, so we have this. One explanation for all this pattern is observations or just power calculations. I don't think it's a big deal here. Sample size is much smaller for RCT and R sample than for the other methods. So if you would think that it's that the sample size is very small, the economists are doing power calculation, they're going to end up with something significant at 5% level because this is what they were looking for. If you do an IV study or diff and diff, you don't do power calculation, especially back in 2012 when these papers, or even 2010 when these papers were conceived. So I really don't think it's explained by power calculation here. The other thing that we do in this paper, so I don't have a lot of time left, is to look at IV. So there seems to be something specific with IV. Again, there's 2 stages in IV. So maybe the first stage helps you to get something significant in the second stage. I don't know that. I don't know how to show you something like this. I don't know whether it's happening. What I can show you is what's happening in the first stage. So I'm going to show you the distribution of F-stat. And again, the critical value, the number that you really want is 10. Now it's getting to 50, or some magic numbers coming from a movie, but back then was really 10. So a lot of these articles are citing this. Stock and Watson, we need 10, we got 10. So I'm going to be looking at whether they get at least 10. So you need 10 or higher, okay? 1/3 of IV papers in our sample do not report their F-stat. Not in a footnote, not in the appendix, they just don't report it. 2/3 do. My guess is if you don't report it, it's because it's higher than 10, but that's just a guess. So here what I'm going to be doing is to look at 2/3 of articles that actually report the F-stat. The problem, some just report once. We have an F-stat of this, they say it in the text, and then they move on, whereas others report it for every single test. What I'm going to do is to put the same weight on every article. And now I'm just going to show you the distribution of F-stat. Some F-stats are really large, 200, 300, but most of them are smaller than 75. So here I'm showing you the F-stat going from 0 to 75. Now obviously what you want to see is at 10. So the next graph, I'm going to zoom in. And if you zoom in at 10, you see that there's a spike at 10, and that most of the action is happening close to 10. There's very few papers, if we go back here, there's very few papers with very small F-stat. Actually, there's one of them, there's like 3 or 4 in our sample. One of them is by Ted Miguel. They found weak instrument, and then maybe they keep trying to get it at higher than 10, but they just gave up. Or maybe they just said, well, it's weak, let's just face the problem and let's deal with it. I think it's the latter, but I don't know that. So, as you can see, there's a lot of action at 10, and there seems to be bunching at 10, okay? Now, what do we do with all this? What we try to show or to document is the extent of bunching, or the extent of rejecting the null hypothesis, exactly at 5% or at 10% level. And we try to relate it to the methods that these authors have been using. Our results are very similar to a recent paper by Alwyn Young, which I really strongly advise you to read, in which he looks at 20, 30 IV papers, and he plays with the data. And what he concludes is that the statistically significant IV results generally depend only on 1 or 2 observations or clusters. These papers have 20,000, 50,000 observations. The fact that it depends only on 1 or 2 cluster observation is quite shocking. And it's very similar to what we find. It's a different way of trying to document this, but the idea is you have a set of specification, and maybe if you have an IV paper, if you don't reject the hypothesis, maybe you just scrap the paper, or you just try to play with your data by clustering in a different way, or by using weights, or by changing covariates, maybe trying to get something significant at 5% level. At least we provide some suggestive evidence that seems to be consistent with what Alwyn Young did find. These results are very important because we might care about publication bias, but we might also care about papers getting published. Yes, might be a subset of all the papers that could have been written, but these papers might also suffer from the fact that there are many false positives. Now, one upside is, now I'm looking at files of all job market candidates applying to my institution. There are tons of RCT and RTD, tons. It's getting way, way more popular over time. So if this is happening, we don't need actually to meet here and talk about like, let's try to make things better. No, maybe we're actually just moving towards methods that seems to be able to produce results publishable by not rejecting the null hypothesis. And that would be really good. Anyway, I'm looking forward to your comments, feedback.